Okay, the first thing you do, pull out your physics books and look at the graphs on page 79. And I want you to write these graphs somewhere into your notes. There's not a space provided, so maybe you do it on a separate piece of paper, and I'll be checking for this piece of paper. Right? If we consider the kinetic energy, we started with this equation, we plugged in for velocity, and then we came out with this as our final equation for Ke. So if we plot Ke, which equals this, if we plot this on the y-axis, kinetic energy, which is really this, and we plot time on the x-axis, clearly we're going to get a sine squared curve, right? It looks like a sine curve, but really it follows a sine squared relationship. Because every x coordinate, right, the way you find the appropriate or the corresponding y coordinate is you plug in that x value, that time, the x value, time, into this equation here for t, and you take the sine squared of that time, so you get a sine squared curve. Likewise, if we do this for PE against time, we started with this equation, and we wound up finally with this equation. So potential energy against time gives us a cosine squared curve, because the way each y value is calculated from the time, the x value, is by taking that value of time, that x value, plugging it in, taking the square of the cosine of the value, times omega, of course, times all this other stuff. But the relationship is a cosine squared curve, because we take the x value and we take the cosine squared of that x value to get the appropriate y value. But what about total energy? Well, total energy doesn't change over time. It remains the same. So total energy should be a straight line, right? The graph of total energy is just a straight line straight across that graph. The y value never changes. It remains the same. The y value remains the same throughout time. And the reason is because total energy is independent of time. We're assuming here that it doesn't decrease due to friction or heat. Right? No friction, no internal energy. So total energy, if we plug in for kinetic energy, plug this in for Ke, right? And then for PE, we're going to plug in this. We see total energy equals, well, we could factor out the sine squared plus cosine squared, right? Because the 1/2 mvo squared is the same. It's not written as mvo, but we know that omega squared times xo squared is vo squared. So total energy is just 1/2 mvo squared times the sine squared plus cosine squared. And of course, sine squared plus the cosine squared is 1. So yes, if we plug in these values, we have just confirmed that in fact, yes, plugging these in and adding them together gives what we previously thought total energy to be. We already knew this equation. This was already, let's see, have we already done this? Yes, I believe we had done total energy, right? We had already said total energy was this, and now if we come down again, look, we get the exact same thing here. Right? So I want you to solve this practice problem. You can pause the video, but I'm going to go ahead. What if total energy is not conserved? Right? Total energy is not conserved. And this is a more realistic scenario because oftentimes there are things like heat or friction which cause the total energy not to be conserved. Well, if that's the scenario, what we have is called damping. Right? So when we first derived those earlier equations, we didn't assume that there was anything dissipating the energy. We assumed that the total energy was never lost. No energy was lost. But in a real oscillating system, we always have friction, and sometimes we have air resistance for a pendulum, maybe, some slight air resistance. These resistive forces do negative work on the system, which results in a loss of energy in the system. So the total energy decreases when we have resistive forces. Right? So this effect is called damping. It's an effect that decreases the amplitude of oscillations in an oscillatory system or an oscillating system. So the amplitude is what decreases when we have damping. The amplitude, right? Yes, the total energy does decrease. Where is it? Total energy decreases when we have damping. But more importantly, we look at damping as something which causes a decrease in amplitude. Right, so what is an amplitude of oscillation, and what does it look like when it decreases due to damping? Well, think of your displacement time graph. And I want you guys to draw this graph as well. Draw a displacement time graph, but not the regular old displacement time graph. The amplitude is the maximum height of the curve. It's the farthest away that the object gets from the zero position. Right? So in this case, the amplitude equals the max displacement, we've seen that before, from the zero position, not equilibrium position. So in damping, and we haven't drawn our graph yet, I'll tell you what to do in a second. In damping, the max displacement, right, which we represent with crests and troughs, hills and valleys, that max displacement becomes smaller and smaller in magnitude as time passes. Right? So here's what I want you to draw. Somewhere on the same page of loose leaf, draw the displacement time graph which would be produced for an object which had some damping. And the way you do this is by making those peaks get successively less big, right? Until we're just kind of a flat line. So I'll do it with my mouse down here. You go up, you go down, you go a little less high up and a little less down, and even less up and even less down, right? And less up and less down. Now these effects can be either weak, medium, or strong. Those are not exactly official terms. But to help us visualize this key characteristic of damping, the characteristic being the fact that it decreases the amplitude of oscillation, turn to page 81 of your book. If the forces that oppose the system, right, if the resistive forces, like friction, are small, then the decrease in amplitude is small and gradual. And we call this light damping. So I want you to draw figure 4.18, which you can find on page 81. Draw that in your notes, either on the same page that we've got going or somewhere else. I might have provided some space. Okay. An example, a real-world example of light damping might be a mass which we have hanging in the air connected to a spring. And the spring and the mass are bouncing up and down together. Normally in that system, we won't have too much damping. It'll be pretty light. Another type of damping is called critical damping. And this occurs when the resistive force is so big that the system returns to equilibrium as fast as possible, but without passing through the zero position. And look, this has to be changed to zero. The system returns to it returns to the zero position as fast as possible without passing through the equilibrium position. Right? So if we have a pendulum that's over here, critical damping means it goes back to the zero position as fast as possible, but it never swings beyond the zero position to the right. If it starts to the left, it goes down and it stops right at the zero position. It doesn't go farther over to the right. No oscillation. Right? So this means exactly what I just said. The object doesn't oscillate around the zero position. It stops moving as soon as it reaches the zero position. Now, in actuality, there are three types of damping. There's critical damping, underdamping, and overdamping. But the only ones that we have to we have to know about for IB are the first two. Right? Light damping is just one example of underdamping. But we're not going to use that term. You don't need to worry about it. I just wanted to explain that there's a third type, which is overdamping. And overdamping is where the object goes back to equilibrium, to the zero position. But it doesn't get there in the fastest time possible. Right? It goes to the zero position. It doesn't move past. It doesn't oscillate, just like critical damping. But instead of getting there as fast as possible, it takes more time to get there. That's overdamping. We call these an overdamped system, underdamped system, and critically damped system. So we only have to know about critical damping and light damping. So I want you to draw figure 4.19 in your notes. Label it critical damping. Now, here's an important thing to notice in your drawings, and make sure your drawings reflect this fact. In critical damping and in light damping, the frequency, which is the amount of cycles, number of cycles per unit of time, that frequency stays the same. So think about what this means in terms of a pendulum. With damping, the pendulum doesn't pass between the peaks, right, between the maximum displacements, any faster or any slower. The only thing the damping does is cause those peaks to become less and less high, progressively less and less high as time passes. So in your drawings, right, you should go up and go down and go a little less up and a little less down. And you should not put your peaks closer and closer together. It shouldn't go up and down and then scrunch up together, right? That would be wrong. Instead, those peaks, the crests and the valleys, right, the hills and the valleys, the crests and troughs, they remain the same distance apart as we move forward in time. So there's cars provide a classic example of damping because they have this thing called a suspension system. Right? A suspension system is really nothing more. It can be thought of as simply a bunch of springs between the body of the car, right, like the frame of the car, and the wheels. So when the wheels hit a bump, they bounce. That's what happens. They start oscillating. Now this causes the springs, which they're attached to bounce. But the springs absorb the shock because they are attached to dampers. There are these other things attached to the springs which very, 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 very quickly and rapidly damp the oscillation. It's a heavily damped system. Right? So those dampers stop the springs from moving, and they allow the car body, which is attached to the springs as well, to not bounce around too much because the springs themselves don't bounce around too much. So the oscillation of the springs really is absorbed by the springs, and it's never transferred to the car's body or the frame. Everything else that's connected to the tires and the axles. So the confusing thing here, shock absorbers, right? The things that absorb the shock are the springs. The springs start bouncing and then they stop bouncing. But the dampers are what we call shock absorbers. So the book says that this is wrong. It might make sense to you intuitively that we should call the shock absorbers, we should label that the dampers. But maybe you think that the springs are what absorb the shock, not the dampers. The dampers are what produce, they're what cause the springs to stop bouncing. So anyway, this is a minuscule point. It's in the book, so it's here. Now we're going to look a little at force vibration, and then we're going to pick this up in class. In all of our previous examples, the system was displaced, and then it was released, producing oscillation. So imagine a pendulum, right? Once it's released, the system starts oscillating and vibrating on its own. I do nothing to the system once I let go. That means it's oscillating at what we might call a natural frequency of vibration or a natural frequency of oscillation. But instead of letting the system vibrate on its own without my outside intervention, I could have given it little pushes at regular intervals. I could have bumped that pendulum every, now and then, every 0.5 seconds. Right? And when I bump it in that way, when I cause it to change directions or bump it, we call that forced oscillation or forced vibration. And it's possible to do this in such a way that the object vibrates or oscillates at a different frequency than the natural frequency. Right? And we're going to end there. We'll pick up with the rest in class.